Welcome to day 11 of Master Data Science in 30 Days by the Data Key. Hello and a very warm welcome to you. This is day 11 of our Master Data Science in 30 Days, brought to you by the Data Key. I am glad you are joining us today as we step into one of the most exciting fields in technology, machine learning. If you have ever wondered how your phone can recognize your face or how a streaming service knows exactly which movie to recommend to you next, machine learning is not just a futuristic idea, it is a powerful tool that is actively shaping our world right now, making our daily lives more efficient, more personalized, more connected in ways we are only beginning to understand. The core idea behind machine learning is surprisingly simple and intuitive. It is the science of getting computers to learn and act like humans do and improve their learning over time in a self-governing manner, by feeding them data and information in the form of observations, real-world interactions. Instead of writing explicit, step-by-step instructions for every single task, we build systems that can learn from experience. This ability to learn from data is what makes machine learning so transformative. It allows us to solve problems that were once considered impossibly complex, from decoding human DNA to predicting global climate patterns. This is a skill that is becoming increasingly valuable in almost every industry. Today, our goal is to demystify this powerful subject. We will break it down into simple, manageable pieces. You do not need to be a math genius or a seasoned programmer to grasp the fundamental principles. Let's begin with our first major category, supervised learning. The name itself gives us a very strong clue about how it works. In supervised learning, the machine learning model acts like a student learning from a teacher. The teacher in this case is the data we provide. Specifically, we use what is called labeled data. This means that for every piece of data we give the model, we also provide the correct answer, or the label. The model's job is to study these examples, the inputs, their corresponding correct outputs, and learn the underlying rule or pattern that connects them. It learns to map a given input to the correct output. Imagine you want to teach a computer to predict the price of a house. To do this, you would first gather a large data set of houses that have already been sold. For each house in your data set, you would have a set of features, which are the inputs. Size of the house in square feet, the number of bedrooms, the age of the house, its location. Along with these features, you would also have the final selling price of each house. This price is the label, or the correct output. The model studies thousands of these examples to learn the relationship between a house's features and its selling price. Once the model has been trained on this labeled data, it can then be used to make predictions on new, unseen data. Because the model has learned the patterns from the historical data, it can now make an educated guess or a prediction about the likely selling price of this new house. This is the essence of supervised learning. One of the simplest yet most powerful algorithms used in supervised learning is called linear regression. We often use it for prediction problems like our house price example. The main idea of linear regression is to find the best fitting straight line that describes the relationship between the input features and the output variable. Now, let's turn our attention to the second major type of machine learning, unsupervised learning. If supervised learning is like learning with a teacher, then unsupervised learning is like exploring a new subject entirely on your own, without a textbook or an answer key. In this scenario, we provide the machine learning model with data that has no labels. There are no correct answers given. The model's task is to immerse itself in this unlabeled data and discover interesting structures, patterns, relationships on its own. It's a form of self-discovery for the machine, where the goal is to find the inherent organization within the data. A very common and intuitive example of unsupervised learning is customer segmentation. Imagine a large retail company that has data on thousands of its customers. What they buy, how often they shop, how much they spend. However, the company does not have any pre-existing labels that group these customers into categories like loyal shoppers, bargain hunters, An algorithm can analyze all the customer data and automatically group customers into distinct clusters based on their purchasing behaviors. These discovered groups or clusters can be incredibly valuable for the company. One of the most popular algorithms for this kind of clustering task is called k-means clustering. The k in k-means refers to the number of clusters you want to find in your data. Our final category of machine learning is reinforcement learning, which is perhaps the most different from the other two. While supervised learning is primarily about learning from a static dataset, unsupervised learning is primarily about learning from a static dataset. Reinforcement learning is about learning how to make decisions through direct interaction with an environment. It is a dynamic process of learning through trial and error. The model, often called an agent, learns to achieve a goal by performing actions and observing the results. It is inspired by how humans and animals learn. For example, a child learns to walk by trying different movements, falling down, and eventually figuring out the sequence of actions that leads to successful steps. A great example to help understand reinforcement learning is teaching a robot to navigate a maze. In this scenario, the robot is the agent. The maze is the environment. The robot's goal is to find the exit. It starts by taking an action, such as moving forward, turning left, turning right. After each action, the environment gives the robot a new state, its new position in the maze, and a reward or a penalty. For instance, if the robot moves closer to the exit, it might receive a small positive reward. If it bumps into a wall, it would receive a negative reward or a penalty. The agent's entire learning process is driven by the desire to maximize its total cumulative reward over time. Initially, the robot's actions will be random. However, over many trials, it will learn to avoid actions that result in penalties and favor actions that move it toward the goal, eventually developing an optimal policy. Now that we understand the three main types of machine learning, let's get a little more specific and talk about three foundational algorithms. First, let's focus again on linear regression. As we discussed, this is a supervised learning algorithm used for predicting a continuous value. Its goal is to model the linear relationship between one or more input variables and a single output variable. The model is simply a mathematical equation for a straight line. Next, let's explore decision trees. It works by splitting the data into smaller and smaller subsets based on a series of simple questions. Finally, we have k-means clustering, our go-to algorithm for unsupervised learning. Its purpose is to partition a dataset into k distinct, non-overlapping groups or clusters. This simple and efficient process makes k-means a very popular choice for tasks like customer segmentation, image compression, anomaly detection, where the goal is to discover the natural groupings within your data without any predefined labels. Seeing the concepts is one thing, but seeing them work in code can make them feel much more real and accessible. For this, we will use Python, the most popular language for machine learning today. One of the most important libraries is called scikit-learn. Let's look at a quick example for each algorithm. First, let's implement a simple linear regression model. Imagine we have some data on house sizes and their corresponding prices. We want to train a model to predict the price for a new house size. In Python with scikit-learn, this is incredibly simple. We first import the linear regression model. Then, we define our training data, X for the features, house sizes, and Y for the labels, prices. We create an instance of the model, then we call fit to train it on our data. Finally, we can use predict to ask the trained model for a prediction on a new data point. For example, training data might be X equals 50, 70, 90, and Y equals 100, 140, 180. To predict the price for a new house of size 80, call predict on. And you might see an expected output around 160. Next, let us see a decision tree in action. We will use it for a simple regression task as well, where the tree learns to predict a numerical value. The structure of the code is very similar to our previous example. Import decision tree regressor. Prepare the data. Create the model. Call fit to train. For instance, training data might be x equals quants 0, 3, 4, and y equals 2, 4, 6, 8. Create a decision tree regressor, call fit, and then predict for input 5. You might get an expected output of 8. Finally, let's write the code for our k-means clustering example. Here we have some data points, and we want to group them into 2 clusters. K equals 2. We import k-means from scikit-learn's cluster module. We then create a k-means model, specifying that we want to find 2 clusters. After fitting the model to the data, we can check the label's attribute to see which cluster each point was assigned to. The expected output might be 0, 0, 1, 1. The concepts and algorithms we have been discussing are not just academic exercises. They are the driving force behind countless applications we interact with every day. Understanding where machine learning is used in the real world can be incredibly motivating because it shows the practical, transformative power of these techniques. Finance and e-commerce. Every time you use your credit card, models analyze the transaction in real time to spot fraud. E-commerce recommendation engines, like Amazon and Netflix, unsupervised techniques, supervised techniques. They analyze your past behavior, what you have watched, what you have bought, what you have liked, then compare you to millions of other users to suggest items you might enjoy. This personalization is powered by machine learning. Healthcare impact is profound and growing. Deep learning excels at analyzing medical images. Models can detect disease signs like cancer in X-rays and MRI scans, sometimes with accuracy that rivals or surpasses human experts. That helps doctors make faster, more accurate diagnoses. Machine learning also analyzes electronic health records to predict patients at high risk. Transportation. Self-driving cars combine multiple machine learning types. Everyday digital interactions. Speak to a voice assistant like Siri or Alexa. Supervised models convert sound waves into text. Spam filters use classification to move junk out of your inbox. These are just a few examples, but they show how deeply machine learning is integrated into our modern world, often in ways we don't even notice. We have covered a lot of ground today, from the 3 main types of machine learning: supervised, labeled, unsupervised, unlabeled, reinforcement, gathered through interaction, a few foundational algorithms and their real-world applications. Machine learning is about teaching computers to learn from data. With modern tools like Python and scikit-learn, you can start implementing these ideas with surprisingly little code. The key takeaway: ML is built on logical, accessible principles. It's a field you can learn one step at a time. So, what are your next steps? Start practicing. Theory is essential, but ML is hands-on. Run the simple code snippets we looked at. Change the data. Tweak the parameters, see what happens. Experimentation builds intuition. Don't be afraid to break things. Every error message is a learning opportunity. Find a small, simple data set online. Try linear regression. Try k-means clustering. Continue following this Master Data Science in 30 Days series. In our upcoming lessons, we will dive deeper into some of these topics. We will explore more algorithms, learn how to evaluate the performance of our models properly, data cleaning, feature engineering. Each lesson builds on the last to create a practical skill set. Consistency is key. Set aside time each day. Thank you for joining me today for Day 11. I hope you feel inspired and empowered to continue exploring this fascinating field. The journey of 1,000 miles begins with a single step. You've taken one today. Subscribe to the Data Key so you don't miss the next lesson. Keep learning. Stay curious. Practice what you have learned. I look forward to seeing you in our next session.